We all may invoke the ideas of risk from time to time in everyday life, with various shades of meaning: danger, dread, probability, uncertainty, variability. And this means that when we're trying to communicate risk in a professional sense, great care is required. Here's a radio interview on the subject of communication of risk. The participants are Sir John Beddington, who in 2011 was the government chief scientific advisor and much concerned with the ongoing aftermath of the Fukushima nuclear disaster, and Lord Krebs, who you may recall was the author of the report on bovine tuberculosis in cattle and badgers. So both had great experience in the consideration of risk. This interview is still available to listen to online. It's worth 20 minutes of anybody's time to hear two heavyweights in action on the subject. Around about the same time, Lord Krebs published a paper on risk and extracted these definitions from the scientific literature. The first three of these are not much use to us because they don't provide us with anything that is calculable. They don't provide us with a basis for modeling risk. The last two do that. They provide us with a basis for a calculation, and they're both in common use. Epidemiologists like myself think of risk as a probability. Environmental scientists tend to think of risk as a probability of an event multiplied by the impact of that event. Both of these are definitions in common use, and what we can see is that even in a technical discussion about risk, we still need to be very careful about how we define our terms. This diagram, based on the National Risk Assessment, is a useful format for thinking about risk. We have a horizontal axis, which is a probability, a vertical axis, which is an impact, and in the National Risk Register, these points refer to outcomes from various large-scale infrastructure failures, from severe weather or pandemic influenza. The fact remains that if we're going to discuss risk in any of these contexts or in the context of crop protection, we have two components that we have to manage: a probability and an impact. And if we can manage either or both of these, where we would like to be is down in the bottom left-hand corner of this diagram. And I'll return to this format later on. Coming up to date, here's a recent review from Science magazine by Baruch Fischoff. The whole article, a review of risk assessment, has a lot of interest for those of us who work in the assessment of risk. But this one particular quotation is important for what I want to say. One common thread, he says, is the importance of collaborative processes whereby analysts and decision makers educate one another about their respective needs and capabilities. And this introduces the idea of shared responsibility for a decision process. And this is something else that I'll come back to. So, risk in crop protection decisions. I'm an epidemiologist. I'm going to talk about risk as a probability, and this is risk at the field scale, at the crop scale. The example I'll use is from the management of eye spot in wheat. This was an HGCA-funded project, and what we have here is the retrospective analysis of untreated crops which underlies the operational decision model. On the left-hand side of the screen, we have a plot which shows the variable that we think of as the threat we're trying to guard against, eye spot at the end of the season, and on the horizontal axis, the decision variable, eye spot at an early disease assessment. And the points on the graph represent 299 untreated crops. For those of you who like the detail of the information, the linear correlation coefficient for that graph is 0.798. Now what I've done is put various thresholds on this graph on the horizontal scale. And those partition these crops into, don't forget this is a retrospective analysis, partition these crops into those that we would have treated and those that we would not have treated. So above the threshold are those that we would have treated, below this threshold are those that we wouldn't have treated. So you can see that a high threshold here partitions relatively few crops into the need treatment category and relatively more crops into the didn't need treatment category. So that's a threshold that would operate for a risk-tolerant decision maker. If we take a low threshold here, it partitions almost all of the crops into the need treatment category and very few into the didn't need treatment category. So that's a threshold that would be used by a decision maker who was risk averse. Now, technically, what happens then is we take the 5 different threshold partitions of the data, and our probability model, based on those 5 different partitions, gives us 5 different disease risk curves derived by logistic regression. On the right-hand side, we see those 5 curves. The top curve is for our risk-averse decision makers. You can see that they've accumulated a lot of risk. This is a probability scale, so this is our risk scale. And this is our decision variable, the eye spot incidence at our early disease assessment. And a risk-averse decision maker has accumulated a lot of risk before even that early disease assessment. The risk-tolerant decision maker has accumulated almost no risk before that early disease assessment, and their decision will then be based on the evidence of that assessment. So we've got a decision tool which incorporates attitudes to risk, which we can see as the differences in these curves before the disease assessment, attitudes to risk, and evidence in the form of the results of that early disease assessment. Note that if we carry out that early disease assessment and the eye spot incidence is very large, then all the disease risk curves converge. So the evidence from that early disease assessment, where the evidence is a high threat, means that the evidence has overridden those preconceptions of risk attitudes, as it should for rational decision makers. The evidence overwhelms the preconception. Now, what do we make of resilience in a decision-making context? This is from a book review that I read recently. It's a very modern understanding of resilience, that positive thinking is perhaps not as valuable as making an honest account of your negative thoughts. So I'm going to make an honest account of my negative thoughts, and that leads me in the direction of not considering reward, but considering its inverse, regret. Regret is the difference in outcome between what we observed from the action we took and what, in retrospect, would have been the best action that we could have taken. We're not interested in regret based on a single decision, but in the long run, and we're interested in minimizing regret. So decision models that offer us low expected regret in the long run are of interest. Note that this means that we can use the diagrammatic format of the National Risk Register, because regret calibrates in the same way as impact. Low is good and high is bad. So here's our diagram in National Risk Register format with regret, our impact analog on the vertical axis, and risk on the horizontal axis. And I'm setting up a scenario here. The scenario is one in which there's no evidence-based forecast. We're making our decision only on the basis of costs. And to start with, our error costs are going to be the same for false positive decisions, treating when we didn't need to, and false negative decisions, missing a treatment when we really should have treated. Risk on the horizontal axis is the personal view of the decision maker, and the graph shows the expected regret lines for always treat and never treat models. If we never treat, our regret is large when risk is high. If we always treat, then regret is large when risk is small. That's how we read that graph. But we're interested in minimum expected regret. So we trace out the minimum that is possible from these expected regret lines. And this gives us a minimum expected regret curve, and for the scenario that I outlined, then the treatment threshold is a risk of 0.5. Treat if risk is greater than 0.5, don't treat if it's less than 0.5. The treatment threshold indicated by a dot on the horizontal axis. Now, usually we don't regard error costs as equally weighted. Usually in crop protection, a false negative error is weighted with costs much larger than a false positive error. So I've drawn on the same plot expected regret lines for the always treat model when the error costs for our decision maker are regarded as twice those of a false positive, 3.3 times those of a false positive, and 10 times those of a false positive. And now I'm just going to look at a sequence of minimum expected regret curves for those different scenarios. Bear in mind that we're using here the same format as that of the National Risk Register, so we would like to be down in this bottom corner here, and at this point here, the peak of the minimum expected regret curve is our worst case scenario. So if we have false positive, if we have our false negatives costing twice as much as false positive decisions, this is our minimum expected regret curve. 3.3 times. Our decision threshold has now gone down to 0.23, and our worst case scenario has moved towards the bottom left-hand corner. If we have false negative decisions costing 10 times that of false positive decisions, then we've moved right down to the bottom left-hand corner here, and our decision threshold on the risk axis is 0.09. Remember, this is only based on relative costs of the different kinds of error we can make. There's no evidence base to decision making here. What this analysis highlights, therefore, is how difficult it is to bring about an evidence-based decision-making approach in crop protection. It's extremely difficult to build an evidence-based decision model which beats this. We have to be right down in, there's very little space left in this diagram to use. This is a very large barrier to uptake of strategies for IPM, because those are by definition evidence-based. So working just in terms of relative costs at the crop scale gives us a barrier to uptake for IPM. Also note how low the decision threshold is for this strategy. If everybody follows this strategy, every individual is risk-averse. We have a population of risk-averse individual decision makers, then that leads to a population level risk of the development of fungicide resistance. The way that we can resolve these problems, I believe, is to take a wider view of the crop protection decision problem than just looking at the crop scale. And this leads us back to thinking about shared decision making. Well, I had my say on shared decision making just recently in an article in the journal Plant Disease written with Fiona Burnett. And what we discuss in that article is ways that we can integrate the experience of farmers, the evidence provided by the crop, and the expertise of people like yourselves. This is an open access article, so I don't really need to say any more about it here. But what you might like to do is look out for examples of shared decision-making that come up during today's meeting. There's more coming up on strategies that lead to the sustainable use of fungicides. There's work on providing an evidence base for the performance of varieties to support local decision-making. And there's work on identifying the key risks for arable business objectives. I hope that during the day you all have a chance to reflect on the themes of the meeting, risk, resilience, and reward, and that it's a productive day for us all. Thank you.